we know that we always need a battery to power a current in any given circuit. Now I have always thought that what if I could have some method by which without a battery I could actually trap current or maybe keep current flowing without a battery. I mean, you know, give an initial push to electrons and then somehow remove the battery and keep the circuit closed and the current will flow. Well, finally I have found a method by which I can actually, without using a battery, keep current flowing for a very long time, and in ideal conditions the current should be flowing forever. So let us have a look at such an interesting circuit. Now we know that, so first of all let us take a capacitor and get it completely charged. So here I have my capacitor and I have completely charged this capacitor, and now let me connect this capacitor to an inductor. Now ideally what would have happened is if I would have connected a resistor or some other thing here, some other load here, a bulb or anything, the capacitor which is charged, let's say this is positively charged right now and this is negatively charged, the negatively charged, I mean the electrons would flow from that side, pass through the whatever the thing is, you know, and reach the other side, and the capacitor would discharge, and you know it would do some work here, the bulb would glow for some time, and after some time the current would obviously, the whole capacitor would discharge and that energy would be dissipated as heat or light, and you know everything would stop after some time because it has completely discharged, and yeah, that's the end of it. But now when I connect an inductor here, now things begin to get interesting. Now let us first of all deal with the mathematical aspect of it, and then we can look at what happens in this intuitively. So obviously I can apply first of all Kirchhoff's loop rule and figure out that the potential difference across the two plates, or rather so the electrons at this side had higher potential as compared to this side, right? So the potential difference here, or the potential gained by the electrons on this side, that should be equal to the potential drop they experience as they go through the whole loop here. And you know this thing has no resistance, so there is no ohmic loss here due to, you know, resistance. All the loss that occurs is due to the potential, the back EMF that is generated across this inductor. So what I can do is I can take the potential difference across the two plates, which would be, you know, Q by C, right? That should be equal to the back EMF of this inductor. Another way to think about this is the voltage. So this capacitor is trying to push the electrons in that direction, you know, due to its voltage, it is trying to push electrons in that direction, whereas the back EMF is trying to oppose that flow, and the voltage of the capacitor and the back EMF of this inductor should be exactly equal, because if either of the two are greater, we would get a net EMF, and because the circuit has no resistance, the circuit would completely blast, right? You would get a short circuit and we would get a very high current and everything would just get ruined. So the back EMF of the inductor and the EMF, or the potential difference of this capacitor, should be equal, and that is what I'm doing here. I'm equating the potential difference of the capacitor QIC equal to L di by dt, which is the back EMF. Now I can shift the L from this side to that side to bring the constants on one side. Let me shift this L from there to here. I get Q by LC, and here I have di by dt. Now I know that the rate of the current, so when the charge flows from this side and goes to that other side to reach equilibrium, we get some current to flow, right? That current is equal to the rate at which charge flows through the wires, and that rate of charge flowing through the wires is equal to the rate at which charge gets deposited at one of the plates, right? So we can say that I, which is current, is the rate of change of charge on the capacitor plates. So what I can do is, and this is the same, this Q here represents the charge on the capacitor plates, and current is nothing but the rate at which this charge on the capacitor plate, the rate at which the charge is reducing, right? So it is reducing from there and reaching an equilibrium. So I know that I can write I equals to dq by dt, right? Rate of which Q is reducing, or rate of change of charge. Now I can plug that expression of current in this here, and what I get is, well, I'll write in the next step, Q by LC equals rate of change of current, but current is dq by dt. So rate of change of charge. So this is a double rate of change of, and so what am I trying to find here? So this expression tells me the rate of change of charge, and this complete expression tells me the rate of change of charge. So this is the second derivative, derivative of derivative, or it is called the second derivative. And this notation here is a very, very messy notation. So mathematicians have come up with a simpler notation of writing the second derivative, which means the derivative of derivative. We can rewrite that as d. So you write 2 there, q, whatever the thing of whose derivative we are taking, of whose second derivative we are taking, with respect to dt square, right? So this is the notation we use to write the second derivative, and this is the expression that we are left with now, which is q by LC equals the second derivative of charge. Now that is fine. Now let me just bring this all to one side, and I'll tell you why am I doing that. Let me bring all this to one side and write it here. So I can write this all of this as the second derivative of charge with respect to time, and I can put a negative sign on this side, but I'm not putting a negative sign on this side. Why? Because I actually missed one step here. Current is the negative of rate of change of charge. Why? Because current is actually the rate at which charge is reducing, right? So I is not dq by dt, I is minus dq by dt, because charge here is reducing. So as this charge reduces, we get some current. So current is the rate at which charge is reducing from the capacitor plates. So that's why I get a negative sign here, and when I take this to the other side, it becomes positive. So I get this term plus that term. So this term plus the other term, which is q by LC, or for now I'll write it in a different way. I'll write it as 1 by LC times q, the same thing, q by LC, and that whole thing equals 0, right? So I've done nothing new but just rearrange the whole equation, and this is the equation here. Now let us first, before moving on ahead, let us come to the intuitive part of it. What would actually happen here if this circuit is made in real life? Well, first of all, this negative charge, so I'll talk in terms of electrons because it is confusing to talk in terms of positive charge and all that. Let's talk about actual current, not conventional current. So electrons would begin to flow from this side through the inductor to the other side, and as they would flow, the charge on the capacitive plates would reduce, the capacitor would begin to discharge. So at the starting of all of it, we have some energy stored in the form of electrical potential energy in the capacitor. So the capacitor is completely charged and the inductor has nothing in it, there has no energy in it. All the energy stored in this capacitor in the form of electrical potential energy. So when the current flows, we get some rate of change of current through the capacitor, obviously, because current begins to increase through it, and that leads to an increase in the flux through it. And because we get some rate of change of flux through the capacitor, through the inductor, that rate of change of flux would actually induce back EMF, and that is what is equal to the potential difference across the two plates. But the important thing here is, by flowing some current through it, we are actually getting some magnetic field in this inductor. And you've learned earlier that when we have a magnetic field in an inductor, some energy gets stored in the inductor in the form of magnetic potential energy. So this actually becomes a magnet and it stores energy, right? So obviously this capacitor releases energy, and that energy begins to get stored in the form of magnetic potential energy in the form of magnetic field lines in the inductor. And that is obvious, right? Conservation of energy. We don't have any resistance, so there is no heat loss, and so all the energy that was stored as electrical potential energy in the capacitor now gets stored as magnetic potential energy in the inductor. And so soon all of the charge gets, all the electrons from here reach the other side, and the capacitor gets completely discharged. Now this has no energy, this has zero energy, and all the energy is now stored in this inductor in the form of magnetic potential energy. And slowly current begins to drop, because now there's no there's no charge left on the capacitor plates, and so current begins to reduce. But now as the current begins to reduce, we know that an inductor does not want a change in the current flowing through it, right? An inductor avoids change in current, so the inductor would now want the current to remain same. It doesn't want the current to reduce. So what would it do in turn? It would produce a back EMF in the opposite direction, and that back EMF would actually support the current. Now in the first first part of all of it, it was the capacitor that was driving the current, because it had charge on it, it had the energy, it was driving the current through the circuit because it had energy. But soon it lost all the energy, it got discharged, and then it is the capacitor that got energy. So now the capacitor would begin to drive the current due to its back EMF, due to the EMF that is generated in the capacitor, in the inductor, and that inductor would drive current through the whole circuit. And because of this back EMF, it would actually begin to charge the capacitor in an opposite polarity. So when the earlier this side was positive and that side was negative, you got some current like this, actual current like this, that so the current flowed in this direction, and as the current began to drop, now so the current was beginning to drop, but the inductor wanted the current to keep on flowing the same direction. So now an EMF got induced that supported the current in this direction, and that current kept on flowing. So these are electrons flowing, and so electrons kept on flowing, and even after the whole thing got neutral, this inductor does not want the current to go back to zero. So its EMF that is being generated in it would actually support the current, and now the electrons would keep on flowing and get accumulated on this side, and leaving a net positive on the other side, and now the capacitor gets charged in the opposite direction, in the opposite polarity. So in this cycle, now the inductor is now actually delivering the energy back to the capacitor. It is charging the capacitor back. So earlier the capacitor was getting discharged and it was giving energy to the inductor, but now the inductor is losing magnetic field lines, it is losing magnetic potential energy, and it is giving the capacitor some electrical potential energy by charging it, by keeping the current flowing in that particular direction. And this is pretty much similar to the case of a spring, to a block attached to a spring, or a pendulum. Let us take the case of a spring. So what I can do is I can imagine something like a spring and a block attached to it at the end of it, and when first of all, at the beginning of all of it, so let us just get back the real polarity. Sorry for the video being long, because I'm trying to put all of it in one video. I don't wish to make two videos separately, because that would break the flow of it. So initially I had negative charge on this side and positive charge on that side. So this is the place we started with. So to begin all of it, I had to first charge the capacitor and put it in the circuit, right? So that is similar to pulling this block from its mean position to some position here. So I pull the block to some position here, I give it some external energy, and that is all the energy that I need to provide to the system to begin the oscillation of this spring block, right? I only need to pull it once, and that is similar or analogous to charging the capacitor only once, and after that everything would be done on its own. Now when I leave it, that is similar to switching the circuit on. So I switch it on or I leave it, that is analogous. Now what would happen here? Electrical potential energy from the capacitor would begin to get converted into magnetic potential energy in the inductor, and you would get some current to flow. Similarly here, the block would start moving, so its velocity or its motion is like the current flowing in the circuit, and the mass of this block is like the inductance of this inductor. The more the mass, so mass actually tries to avoid change in velocity, right? A change in velocity. If you have a higher object, it would take more force to change its momentum or velocity, so to speak. And similarly, an inductor opposes the change in current. And so they are analogous, mass and the inductance. and the spring here is analogous. So the block was analogous to the inductor, and the spring is analogous to the capacitor here. And you know, if you remember the K of a spring, the spring constant of a spring is similar to the capacitance of a spring, capacitance of a capacitor. The higher the capacitance, the more energy that is stored in the given capacitor. Similarly, the higher the spring constant, the more energy you get in the spring. Why? Because it is a harder spring. A higher spring constant means it is a very harder spring, so it would pull it with a higher force, and you would get more energy stored in the spring. So let's continue. The block would keep on moving in this direction, and the potential energy stored in the spring would get converted into the kinetic energy of the block here, which is analogous to the electrical potential energy that is stored in the capacitor, that is being converted into the magnetic potential energy in the inductor. So I hope you can join the two things. And now it moves and reaches its mean position here. At the mean position, all the energy is stored in the form of kinetic energy, and there is no potential energy. That moment is analogous to the moment here when all the energy is stored as magnetic potential energy in the field lines of the inductor, and there is no electrical potential energy in the capacitor. Now it keeps on moving ahead due to inertia, which is similar to the inductor driving the current, because it doesn't want to change, because it does not want the current to reduce. Just like the mass doesn't want to change in velocity, it doesn't want the velocity to reduce, and with inertia it keeps on moving forward. And as it moves forward, it compresses the spring, and the kinetic energy of the block gets converted into potential energy of the spring. Similarly, as the current moves on forward, it keeps on moving. The current actually charges this capacitor, and the magnetic potential energy in the inductor gets converted into the electrical potential energy of the capacitor. So I hope you are getting the sense of it, how these two situations are very analogous, and their mathematics is very analogous, very much same, only the variables are different. And if you imagine them, what would happen in this situation? Once I pull it and leave it, it will keep on oscillating back and forth, and kinetic energy and potential energy would keep on switching. So for some time you will have kinetic energy in the block, and on the other on other instances you would have potential energy in the spring, and this would all keep oscillating back and forth. You would get KE, PE, it would keep on oscillating. Similarly here, the charge would keep on oscillating back and forth, and the energy that was stored would keep on getting transferred from the capacitor to the inductor, and vice versa. And it would sometimes be stored as electrical potential energy in the capacitor or magnetic potential energy in the inductor, and it would keep on happening. Now one final thing here to add is that this expression here is pretty much similar to the motion of a block attached to a spring. And if you remember from last year, that motion is called simple harmonic motion, and the equation that governs the motion of an object under simple harmonic motion, that is pretty much analogous to the equation that is written here. So I'll just tell you the equation here. The equation is d square x by dt square, second derivative of displacement of the SHM or the block, plus you would get omega square x equals 0. Now another analogy you can draw here is that it's the second derivative of displacement here, whereas it's the second derivative of charge here. So displacement in an SHM, in that spring block case, is very much analogous to the charge stored in this case, right? And the rate of change of charge is current, whereas the rate of change of displacement is velocity. So I hope you can draw the analogies there also. And one clear thing that you see here is that this term and this term look good. This term and this term, so x, we have x here, and we have charge on that side, analogous, which means that this term here, omega square, so omega is nothing but the frequency at which the SHM moves back and forth, that is pretty much analogous to this term here, 1 by LC. So what I can do is I can infer that the frequency squared equals 1 by LC. So I'm inferring this thing from the by comparing the two equations. And this omega naught, or this frequency here, is the frequency at which current in the circuit keeps on oscillating. So it would oscillate at a natural frequency, just like when you pull a spring and leave it, it oscillates back and forth with some given frequency, which is its natural frequency. Similarly here, when you charge the capacitor, put it in place, the charge would keep on oscillating back and forth with a given natural frequency of this particular circuit, and that natural frequency is given by this expression here. I can shift the square from this side and get it there. And this expression here that I have, this tells me the frequency of this circuit here, and you can call it the natural frequency of oscillation of this particular circuit. And because the current oscillates back and forth, this is generally referred to as LC oscillations. And this is a very beautiful concept, and I'd suggest you to spend time with this by looking at the equations and imagining what would happen. You can imagine it yourself also, and comparing it to the case of a block on a spring or a pendulum, and you can yourself realize there are so many analogies that you can draw, and it will obviously help you in understanding the whole concept much more deeply and clearly. So yeah, and obviously you can also refer to the book, because the book has diagrams that will show you how you can visualize these two better. So yeah, that's it for this video, and I hope you get a better idea of this through this video. That's it for this video.